Our next speaker is Stefan Winkler. Stefan Winkler obtained a Master in Control Engineering at Vienna University of Technology in '94, and after having performed his civil service, was appointed as a research assistant on water quality monitoring at the University of Georgia in USA with Professor Bruce BECK. Since '98, he's a research assistant at the Vienna University of Technology, the Institute for Water Quality, and his main topics are long-term continuous monitoring, wastewater treatment processes, and wastewater treatment plant staff training and education. In the period '98 to 2005, he also had a 50% employment at the VIATEC WABAC. It's for international wastewater treatment plant tendering. Stefan, the floor is yours.
Okay, thank you very much. Good afternoon. I will present the monitoring platform this week. Today. I start with an overview. I will give you some impressions that we got from practice. How is the state of the art in water monitoring, with some bias in how it is used in wastewater treatment plants. Then I will present our monitoring platform. And finally, how is this working? Okay, I will, sorry?
You point to the back.
I point to the back, okay. I will show you some utilization of automatically validated data, how that can be used in practice, or how that can improve your daily work with data. Okay, so how is the state of the art? I mean, maybe it's a subjective observation, but that's at least what we see in Austria or in neighboring countries of Austria. There are some alleged trivial aspects, but in practice, often these aspects are quite some substantial bottlenecks to work with your data. For example, time-based assignment, from internal sources and even much more from external sources. You get some data sheet with time. Okay, is it UTC? What is it? It's not really documented. If you work with online measurements, you have the measurement controllers of different manufacturers, and most of them have quite some limitations. You have no chance for an external time synchronization. Usually you don't have a chance for an external trigger mode, or very rarely, so the instruments run on their time base of that controller, and every controller runs on his own time base. You don't have any event coordination, often not even on the same instrument, so maybe you have one instrument that runs into a cleaning cycle with pressurized air, and then the controller holds that signal of that specific instrument. But if you have an instrument installed very nearby, you have the disturbance from the air bubbles, and not even the other instruments that are connected on the same controllers get a signal hold during this period. So you get some kind of artificial signals during these periods. And most of the loggers have controllers have some kind of internal logging. Mainly it's text-based, but every company has their own format, and if you run a station with several controllers, you end up with 5 or more different formats, and pulling this together by hand is possibly not really possible. If you want to integrate different products, the only way that you can usually do it is by analog signals, and then you have all the problems with analog signals. For example, if you want to integrate a flow measurement, the question arises about signal scaling. Do you want to catch the peaks? Then you are most of the time at very low, at the very lowest range of the measurement range. If you want to optimize for most of the time, then you cut off the peaks. You only get the signal itself. You don't have any meta information from the instrument, and you have a very high cabling demand. So really very simple installation can be done on controller basis by itself, and if you have a more complex application, you need some integrated hardware and software on top of it. If we look at the data use, how is this done? Usually in practice, most systems are just data collectors and also visualization, and if there are some specific, very extraordinary events, these are detected or displayed in a SCADA system. But really, data checking, plausibility checking is not really an integrative part, or it's only included in the post-processing stage. So the data are collected and then with a quite significant delay they're analyzed and then they are looked for errors. There is a lack or an improper application of automated tools for quality assessment, and this ends up that you do not see any potential faults in your measurements, or only a long period after they have occurred. You don't really know the circumstances that lead to this error. Was it an instrument problem, or what was the problem? Often the metadata is not available, or it's not sufficiently documented. And then you cannot really distinct instrumentation problems from real system dynamics. So you have a potential risk of an incorrect data interpretation, and if you consider there is quite some cost involved with operating monitoring networks, you might end up with a data-rich information pool situation, and that's not really what you want. How I approached what we developed at our university is this monitoring platform called iTUWmon. It's nothing to do with Apple, so it has this I in front. It stands for Intelligent Information Water Monitoring Networks, and since there are two I's, we choose the acronym of our university, TUW, which spells like two for the two I's. Okay. So, what were the key development goals? We want to maximize the availability of plausible data that you get from a monitoring network. We want to have a near real-time detection of operational problems with the monitoring stations. We want to have an automated information extraction from our data. And we want to have minimum maintenance in the field. Last but not least, I show it at the very end, this system is also based on complete autonomy from the power supply of the station. So we have a station with solar power supply, and also that everything regarding the data can run locally without the demand of having a high-speed internet connection to that monitoring station. And we can still then transfer everything, but the system is autonomous on the spot. What are the core functions? Just to name a few, we have a unique definition of all the variables within a network, so it doesn't occur that whatever flow or lever is named with a certain symbol is one station and with a different symbol in the other station. We have an event-based measurement cycle control. We have several operating modes, so a general measurement mode, a triggered mode, and a maintenance mode. We have a data format which is independent from the manufacturer, from the type of instrument. We have an instant data check on the station. We have metadata integration, user information, and we even check for data logging completeness. So, more in detail. Every measurement cycle is triggered as a specific time point, and all the instruments are running on this same time point. We even consider the time delay of the instruments. So if you have instruments with very long delay time, the whole cycle control considers this. And we have a network-wide time synchronization. The mode control, we adapt to changes of the dynamics of the observed system. So we increase, for example, the measurement frequency, or we trigger an automatic sampler if some specific events occur. We flag the data according to which mode they have been generated, and we have also a maintenance mode that can be started by hand. We have this event-based measurement cycle control, which is an adaptive scheduling algorithm. We adapt to the system dynamics in the way the whole system is run. We have event collision logging, so we cannot have one system in one instrument in measurement state while the other one is cleaning, for example. We make up missed cycles, for example, if we have to speed up the measurement frequency because one event occurs, then we might postpone a cleaning cycle, but we try to keep that up at a later time if it's possible. And last but not least, we have a manual operation mode also. How does this look? For example, we can also include data checks, very simple statistics checks which are given in a text-based mode, so that it's not also possible for expert to parameterize those plausibility limits, or we can implement dynamic limits for the plausibility, for example, if you have a parameter that follows a dilution function. The results of these data checks are shown in the main window in a kind of traffic light approach. So if you look at this window, you immediately see if you have a lot of problems or not, or if the system is running okay. And last but not least, we also check for data completeness. In this example, we get data from an external base, and if this transmission is not working, you also see it in the main window that the transmission of this data has not worked. What you also see here in the example, as I mentioned before, these are two examples of flow data, and you see they all have an unique symbol, so it's consistent throughout the whole network. User information, for example, from this window, you have this button where you can manually change to the maintenance mode, and that's also shown above here. And in the automatic mode, it changes between the general measurement mode and the trigger mode by itself, depending on the system dynamics and the definition of the trigger conditions. You see what's coming up next, and you see how long those events will last. So you have a text message here where the time is running, and you have this bar representation in addition, and you have all these buttons for the manual operation of the station. User information, for example, how all the instrumentation is connected to the system. You have all the instruments there and the serial numbers and the type of interface and the scaling and all this information. And from the serial number, you can track the instruments through the whole network, and you, for example, can see if a specific measurement method is good or not so good for a specific type of application if you run these parameters with different instruments in parallel. Metadata integration, I mean, the main point here is that you have it at hand when you need it. So we integrated it into the system. Hello. Okay. So I can ask for the data sheets, and I get a list of the available data sheets, for example, and I get, for example, a calibration information for a specific instrument right at hand on site. Okay, so now in the following I will try to give you some examples on how you can use this or how we use this. As I showed you before, we are running basic checks on all the data sets right after we have collected the data, and this is a comparison of the distribution of pH values at two different rivers. And what you see here, at the first river you have two different monitoring locations, and the average pH decreases over the length of the river and the variability increases. And in comparison, these right two boxes are the same river in two different years, and in this year the flow was much higher, so you have more solids transport in this, and as a consequence you have lower photosynthesis activity, and therefore you have less variability in this year compared to that year. And of course it's much better to have plausibility limits that adapt to this situation, and that you don't put, for example, 7 and 9, then you cannot really distinct anything between your locations. Also, if you look at the dynamics of the pH value, for example, you see from two different locations that you have quite a different distribution of the variance, or sorry, of the speed of change of the pH value at these two different locations. This is an example for this trigger mode and how you can adapt to the system dynamics. We have two rain events in a row, and the system took 19 samples within the first 9 hours, and then only 6 samples within the next 24 hours. And if you zoom in, you can see that even this quite fast event was triggered quite coarsely. A comparison of DO measurements. We can look at the absolute concentration here in winter and in summer. And if you compare this, okay, if you're an expert, you might get a lot of information out of this, but mainly you see, okay, that the concentration in winter is quite the same between the two locations, the upper and the lower locations, and that you have quite a high variability in summer compared to winter time. But if you only look at the absolute concentration, you don't get as much as information out as if you look at the saturation deficit now at these two locations. From this we see that in winter we have a continuous deficit at both locations during winter time, and that we have some higher degree of saturation deficit at the lower monitoring location. If you look at summer, it's a quite different picture. You see that you have now an oscillation between oversaturation and saturation deficit at both locations. At the lower, it's much higher, the dynamics, and you see that with increasing temperature, if you look at the daily average of this DO saturation deficit, you also see a slightly decrease over the week. At the lower monitoring location, you first see an increase and then you see a decrease over the week. So, yeah, it's almost the last one. And if you compare the winter and the summertime, you see that in winter you don't have very much difference between those two locations. In summer the upper location follows quite this, but you have a longer photosynthesis period due to the extended daylight situation, and you have a phase shift compared to the lower monitoring location. Okay, so I skip. Yeah. Okay, I skip this one. And just to mention it, we can also integrate this power data. For example, from such a graph, we can follow the charging and discharging cycles of the batteries. Okay, summary. Due to a lot of circumstances, it's required to have an overlaying hardware and software to really run such complex monitoring systems. We showed that data quality assessment is quite important. It's not really so much used in the practice at the moment. And maybe last but not least, I hope I showed you that if you have some system of automated information extraction from your data, it can be quite a valuable base for improved system understanding. Thank you.
Thank you. Thank you. Thank you for this very interesting presentation. Unfortunately, the time will leave us for questions and negative. Positive aspect is that you already answered the first question, what the 2 stands for in the title. But let's allow at least 1 or 2 short questions.
I'm Kim van Scharen. Just out of interest, so you show the software, but developing this box with the solar panels on top of it was also part of this project.
Yeah.
What was more challenging?
Sorry?
And what was more challenging, the hardware or the software?
Everything.
One last question.
Well, the box was a monitoring station, yeah. So in the box is a complete station with suction pump and everything.
Yeah, Stefan Weijers, the Netherlands. This is hard and software, but did you produce it for your own purposes, or is it something that you also intend to have a company to do it for other parties?
Well, I mean...
What is the status of that?
Yeah, okay. How can I say? Well, we developed it because we didn't really see that there is anything available on the market who really does it like this. And we tried it with some companies beforehand, but this was, to be honest, always a nightmare. Well, we are a university institute, so we are very interested in cooperations, and I think we learn a lot if somebody else uses it. But we are not like a company who sells it. So we are very much interested in projects in whatever constellation. And I guess it's quite important that other people use it and that we get feedback that it's not now. So far we only used it in research projects in academia. And I guess if people from practice are using it for different purposes, it would be quite a step forward.
Thank you. I think it's a good conclusion. Thanks for this contribution.